I'd like to introduce Peter Vojta. He's a research scientist at Facebook. He has 2 master's degrees and a PhD from EPFL, which is in Lausanne, Switzerland. And he also worked in a group at Stanford, my alma mater, where he was working with Bernd Giraud, the professor that was working on video compression and things like that. Peter's title today is Building Efficient CNN Models for Mobile and Embedded Applications. Please welcome Peter Vojta.
Thank you very much. Hello. I hope you enjoy the talks. Today, I'm going to talk about efficient deep learning and computer vision algorithms for embedded devices. I'm Peter Vojta, leading the mobile vision group, research group at Facebook. So most of the research focus on improving the accuracy, like pushing for a challenge in ImageNet. But it's not necessarily enough for running these kind of models on real-time on mobile phone. And embedded devices, you have to optimize for other axes as well, such as speed or memory size or even just the model size itself. And you have to balance between this group of axes to make sure that your model, what you run on phone or embedded devices, is running real time, very efficiently, and then you can download the model from a cloud or store it in a mobile device, which is very small and compact, and don't take up most of the space on application. So in this talk, I will describe first some of the model architectures which is out there, especially MobileNet from Google and ShuffleNet. Then I'm gonna discuss a little bit about how to compress these models into the smaller space by quantization and then pruning. And then at the end, I'm gonna describe a couple of or 2 different applications that we pushed out from research to product in Facebook, and then accessed billions of people with this kind of applications. And probably it's in your packet as well right now. One of them is time transfer, and another one is a real-time key point estimation or pose estimation for people. So let's start a little bit with state-of-the-art architectures and some of the improvements, so making some models very efficient and able to run on mobile phone. So I'm going to introduce here MobileNet. MobileNet is developed by Google. It's a very efficient network design specifically for mobile devices, which has an idea how to actually make models more compact, more efficient. And the main idea is to decompose the convolution for 2 different layers, like a depthwise convolution and the pointwise convolution. While depthwise convolution is running a convolution by each channel separately, pointwise convolution is a very small one-by-one kernel size convolution. And using combination of these 2 can have a very efficient and faster building blocks for convolution. In the right side, you can see some of the little bit more detailed analysis of how much time it could compute, or how much computational time is needed for different layers, such as for convolution, where DK represents here the kernel size. It's usually 3 or 1 by 1 or 5 by 5. In inception event can be 7 by 7. And N and M and input and output channel size, where you use a standard convolution. It's compute these kernels for each input channel, for each output channel. So it's lots of multiplication there. And over the flops, you can calculate like multiplying by the channel size, dk, by the input-output channel size, n times m. And and of course the activation feature of size, which is denoted here as DFDF. So a general convolution algorithm in theory takes like this amount of computation. While using depthwise convolution, you apply this convolution channel by channel and not mixing up input and output channels. So therefore, running this convolution, you can save like n times the computation. But of course, it doesn't communicate the network between channels. And then you need to solve this by other way. For example, using pointwise convolution, where the difference for normal convolution is using 1x1 kernel size. Therefore, the speed up compared to normal convolution in 1x1 pointwise convolution is depend on the channel size, because dk here actually is denoted and then used 1x1 in 1x1 convolution. So overall, replacing normal convolution with depthwise and pointwise convolution, of course, it's speed up the networks, because n is usually hundreds or more than 10. The most computation in this case still is the pointwise convolution, which reduces the computation by 9 in theory. And that's going to be the bottleneck of computation. Overall, it's a great speed up. The accuracy obviously is dropped a bit, but you can apply the faster architecture and more deeper and better networks. The other part what actually this paper proposed is to do hyperparameter search on this kind of networks and varying two different parameters. One of them is the width multiplier, which just changing the channel size with different constant ratio, while the resolution of the input, which can be varied, and then it's produced many different models, and you can balance out what is the best model that you would like to choose for specific limit of memory and size. Moving a little bit forward, when you apply these kind of changes, you still see that 1x1 convolution is the limit of these networks. While if you apply it in mobile devices, you realize that, for example, depthwise convolution, the memory band is the limiting factor instead of compute. So therefore, you cannot really get exactly the same theory speed up what you can get from theory, but it's definitely with specific hardware optimization can go forward and then push forward for the later to the getting the limit of the theory. Little bit discussing about ShuffleNet. It's an other idea when we discussed about that pointwise convolution actually taking most of the compute. Same as like ResNext or MobileNet, like 1x1 compute actually taking 93% of the time of the processing time. So therefore, you want to optimize a little bit this further away. If you use group convolution, even on a pointwise convolution, you can speed up the 1x1 convolution. In a figure A, you can see if you apply the same group convolutions along the way, the channels actually won't be like communicating with each other. They won't have any like improvement over each other and well separated along the whole network. So therefore, ShuffleNet proposes a layer called Shuffle layer, which is actually parameterless network layer, computes really fast. It's only just shuffling the channels into the network. Therefore, after group convolution, you can mix up and then have a cross communication between different groups. So this is a little bit comparison of general ResNet model when you use depthwise convolution. you apply one-by-one convolution to mix up the channels. In ShuffleNet, you can use one-by-one group convolution, which speed up the network, and then no-time channel shuffle, which communicate between the channels. So this provide a great speed up and then keep the good accuracy of the model itself. Little bit of overview of different networks. Since then, there are some of the state-of-the-art improved already in ShuffleNet and MobileNet. Overall, what you can see here that there are general networks, ResNet and GoogleNet, which optimize for more accuracy, require more flops and more computation on the time. You cannot run them real time on mobile phone, but there are specific network design, what we discussed, like MobileNet, SqueezeNet, or ShuffleNet, specifically for mobile device. In the x-axis, you can see the computation in flops. In y-axis, in top one accuracy on ImageNet. So let's talk a little bit on how to compress these models. Let's say you want to put this model into the mobile application, then it takes several megabytes, and it's not really efficient to store there. If you want to download them from cloud, there is a bandwidth that you can utilize, and then smaller network definitely give more reliability downloading very fast these models. So the very first and very important part is pruning. These networks that you train usually are very redundant. Losing out those weights and not considering like zero close weights, you can save lots of storage as well as a memory size reduction. In this case, you see general pruning of each weights where the weights are very close to zeros. The good part in this is that if you start pruning or quantizing the network, you can even realize that the accuracy increase some points and then start dropping suddenly. In terms of quantization, you can store the weights based on clustering. Store only the cluster centers, compress that, and store only the index for these different clusters. When you are training these models, you can update these cluster centers as well as the weights itself. In this figure, you can see some of the experiments, what you can see with different quantization and pruning. Usually, if you see papers out on quantization and pruning, you can see like 70 or 50% improvement in terms of compression. Obviously, if you run very redundant, very big networks, then this is the case. If you run very efficient and small networks, like let's say MobileNet, SqueezeNet, or ShuffleNet, still you can get lots of improvement in terms of quantization and then model reduction, which is very interesting, though not 50 times. In this case, like we were able to, in a very small network, we can prune away 63% of the parameters and do quantization during the training by 8 times, producing 8 times smaller network. Here in the x-axis, you can see the quantization bits and then information what stores, and in the y-axis is the top accuracy compared to the full model. But the interesting is this curve you can see in blue and then the green, that top 1 and top 5 accuracy, it doesn't start dropping actually the accuracy even for 8-bit networks. And if you consider a little bit less quantization, you can even increase the accuracy. So we can generally say that even in a very compact networks, which is still redundant, you can compress the network like 8 to 10 times more to reduce the size. So because of this kind of interesting insights that with the quantization and pruning, you can even increase the accuracy of the model, there is a very interesting research direction which pushed out to doing dense sparse dense training method, where you start training the model with full all the weights. Then along the training, you quantize the networks and pruning away some of the zero close weights, and then slowly getting back and learning back the weights what actually you removed can increase the accuracy itself. This dense sparse dense training in generally applied also in speech and then many other techniques. You can increase most of the networks by 1 or 2% accuracy. This is ImageNet numbers compared for the same training process with the top one error versus dense sparse dense training error. You can see in GoogleNet, ResNet 50, you can get 1-2% improvement on ImageNet on computer vision. Similar applies for speech and other techniques as well. So just a little bit summarize this part of the talk about model optimization approaches. I didn't talk any kind of every approaches, but here is a little bit of the summary, what we use and what we apply. Obviously, you don't need to only optimize for accuracy, but you have to consider and balance away the speed limitation of the mobile phone and the size of the model itself. So in terms of accuracy, we described as dense sparse dense regularization. There is a very important part what I haven't talked about, distillation. When you try to train a big network, a small network with a big network, this can get a couple of % improvement for small networks. Also, improving the speed is very important to optimize a model specifically for the hardware, or vice versa, pulling up and then creating very good hardware for the model itself. Architecture search is very important aspect. As we see in a mobile net, there are some hyperparameter search as well. It's very important to fine-tune this kind of parameters, and it can get actually very big gains. Other aspect is low precision networks is getting, as you see, a couple of the presentation before and then some of the showcase is getting more and more important in production level as well. A low precision network, I'm talking about, let's say, 8-bit networks, and you see already like 2-bit network or 1-bit network in the showcase booth. For reducing smaller size, we discussed about pruning and quantization. Let's go for 2 specific products what we pushed out from research. One of them is real-time style transfer. So style transfer is not a new topic, and it's not started in 2015, but much earlier. This is the first time in 2015 when deep learning actually applied for style transfer by Gettys. The goal of the style transfer is to have content and style image and produce a new image which actually apply the style from the style image and then on a content which was presented in a content image. So you apply this Gettys paper, which was very great research and then showing stunning results. You run iteratively a VGG network over to optimization for this image. It takes like a couple of minutes, even in a very good GPU. Then the follow-up paper with Justin Johnson, where he applied actually this VGG network as a loss function to a new network called Image Transform Net, what used for doing the style transfer, where in this figure, X is the input image, goes through the network, producing Y hat. Similar like a content target and style target image, and then go through the VGG loss network, and from matching up as a loss function, minimizing the difference between Euclidean difference between the content target and the output of the Y hat on a specific layer, more on the end layer of the VGG network, which represents more content information. And with the style itself, multiple layers, especially for the early layers, using the difference, not the difference, but the gram matrix of the channels of the feature space in the VGG network, and propagating back those loss functions through the image transformat. Why this image transformat learn how to produce y-hat, which gonna be more similar to the content and similar to the style itself? It can produce a network which produce this style very efficiently. And you can imagine that this image transformat can done in a very small, very efficient network manner. For example, using UNets, reducing the channel size and the weight and the depth of the network, and you can create a very efficient small network using compression and pruning, what we discussed before, and then you can deploy it on a mobile device real time. This was the first time when we created Café2Go. It's an open source network and framework where you can run real-time neural networks on mobile devices, very optimized for CPU, GPU, and DSPs. Running on high-end phones, usually you can run this style transfer, and it's already on your Facebook app. The difficult part in style transfer was actually the evaluation. It's very difficult to evaluate the quality of the output of the network. Here, in this case, like lots of A/B tests and lots of user experiments have to make done to choose actually what's the right style and what's the best actually network what we can put out for production from the research. This is some of the interesting video. That's me, actually. And some of the team members from Facebook worked on style transfer, created this real-time style transfer, and Café2Go shipped and open-sourced 1.5 years ago. And the Facebook office, obviously, you have very nice benefits with the free ice cream. That's the most common way to get fat in Facebook. So next part, I would like to discuss a little bit about pose estimation. This is a little bit of follow-up work on real-time style transfer. Here we do real-time key point estimation on the phone itself. It's also shipped F8 some of the effects for that, and fortunately, we also open-sourced the whole training code, the efficiently optimized layers necessary for running real-time key point estimation on mobile phone. So if you want, please go ahead with the Café to train your own on key point estimation or segmentation models, and you can deploy it on mobile device very efficiently. Same what Facebook actually using right now. So these are the layers that I optimize very well. Generate proposal. We're going to describe a little bit where these layers are applied. And then there are lots of use cases for key point estimation. One of them is doing gesture recognition real time, or understanding what on the video, what people want to achieve, doing specific AR effects, or controlling your avatar with your key points. And I described about Café2Go, which is open source and very efficiently optimized for these layers for CPU, GPU, and then DSP. A little bit more about technical details. The input image goes through the network, which actually cropped out the objects proposed by region proposal network, then running refining these bounding boxes, and then create a classification. And then at the end, there are key points and segmentation head that actually run for the network and producing the results that you want. The key part from this network is the region proposal network, which using different anchors in some aspect ratio and different position of the network, proposing generally object bounding boxes. After these bounding boxes with ROI pool, or ROI align, you crop out the feature space from the trunk network, and then continue to do a classification, detection, and segmentation on these networks. We describe about like open sourcing this. It's run real time on high-end phones. The network itself split to like mobile net or any very efficient mobile network can split in different parts in a trunk or key points and segmentation head and detection head. By doing this very balanced way, you can make sure that the efficiency is very well suited for mobile device and apply the similar techniques that I mentioned before about designing a very small network, pruning quantization, and splitting up, designing balanced networks for heads and then detection and then trunk. This is the heat maps showing out from the output of the feature maps. You can see for key point actually, red highlights some of the key points. For example, head, nose, ears, or legs or knees, where the value of the heat map scores high, propagated back by softmax. After post-processing these heat maps, you can derive what's the refined coordinate in the body, what you can use. This is generally for COCO datasets, which use 17 key points. You can imagine you can put much more key points there and then do way more part. There are lots of challenges here, specifically if you want to put something on a very good way on mobile device. Is very important to produce very good training data, evaluation data, and testing data. Besides that, I talked about here flops and max. Usually optimization this for mobile devices or embedded devices is a good indicator where you can improve and how you can use a very efficient network. Though the most important part is actually the real-time evaluation on a mobile device or embedded devices, where the layers actually not similarly efficient compared to what flops suggest. And this is just a demo video. So you can run this on your phone, and if you have a Facebook, you already have this with the butterfly effect or some of effects that actually applied, running real time on high-end phones or good phones. A little bit about future work. Definitely, architecture search is going to go along the way, optimizing specifically for hardware, optimizing hardware specifically for the needs. Is very important to push forward in research as well. Also, like leveraging the very efficient layers that we open source with Caffe2, and make sure that those applied well with this kind of networks is a really key to push forward, as Facebook is really into open sourcing the technologies what we have, what we apply actually in a production for billions of people. You can use it right away. Just go to the Caffe2 website. Some of the takeaways what I didn't talk about, but that's the most important part, is data for training, data for evaluation, and data for testing. Most of the improvements actually came from data. In production or in research as well. Very high and accurate annotations and data actually is the key for creating very good deep learning models. And then obviously, you probably know already this. Other aspect, what I didn't go into detail, is a Caffe2 optimization, what we push forward and open sourced for high and low-end Android and then iOS phones for CPU, GPU, and DSP. Everything is open sourced, and then there are very great tutorials all together with PyTorch, where you can train your own network and do a research, and then run real time on mobile phone or embedded devices with Caffe 2. We discussed about some efficient model architectures, such as accuracy, optimizing for memory size, and of course, for speed, and balancing between these. There are some different trade-offs running something on mobile device, on the cloud. Both has very great benefits. If you run on mobile device, these networks, you can run a real-time interaction. You don't need to have a very good connection to the network itself. But the most important part is you don't need to send any information or any images or any information from the network, because you can run anything on a mobile device. So there is no privacy concern on running like this mobile and very efficient models on device itself, because you don't send anything to the server. Though in a cloud base, you can save on your battery, because it's just sending the image itself, or in a hybrid way, some features. In low-end devices, cloud is the only option sometimes, where you cannot run these very big, deep networks on low-end mobile devices, as well as limited accuracy for mobile device. The compute is limited compared to the beefy GPUs or CPUs that you have in a cloud service. There are benefits between both running on mobile device and on a cloud service. And there is a third, which is a hybrid application that you can push forward. Let me give you a couple of information about a couple of links that you can follow up a little bit more on the application and research. My name is Peter Vojda. This is my page at the beginning, and then there are 2 blog sites that we pushed out, and a couple of papers, like Maskarssinen is actually won the best paper award last year in ICCV. You can look it up. That's what's actually producing this key point estimation. On Caffe 2 Go, please go ahead and then read about style transfer or Maskarssinen 2 Go. Both of them is open sourced, all of the layers. And you can run it real time on phone. Thank you very much.
Thank you, Peter. I had a few questions.
Yes.
I hadn't seen the dense, sparse, dense concept, and I was, this is probably a newbie question, but why would you prune something to remove nodes and then add them in again?
Yes, so when you start and training a network, this is a lot of process, and it create actually a very redundant network itself. By pruning out the network itself, you realize that even just quantizing the network or pruning, it's increase the accuracy itself. So pruning already with certain level, you can increase the accuracy. Learning back the new layers from scratch actually helps training that as making them more meaningful and more useful in the network. So lots of this redundancy can move away with pruning and quantization, and brought it back to learning some new insights and new interesting part from the network. This is the hypothesis. Obviously, neural networks is a very mysterious, very interesting beasts. It's worked pretty well in practically as well as in modern in training, and then that's what our insights for this dense sparse training.
Okay, good. One other is kind of a practical question. Like if you're using a mobile phone for doing face recognition, there's some practical reasons for doing that, like using it to unlock your phone instead of a 4-digit code. What are some of the practical uses for this pose estimation, aside from taking pictures of your friends when they're dancing?
Yes. So one of the couple of applications in the AR space or VR space can be, for example, you can do some of the AR effects and take a nice picture, post it in Facebook with different effects with you on body, or using together with segmentation. You can replace yourself with avatar. It's pretty useful actually when you wear these big Oculus headsets and then actually the whole body is not shown, just some camera. So recognizing what you're doing and then replacing yourself in a VR space with avatars, that's a pretty important part and an important aspect, that you present yourself as a full body in the VR space. And obviously, one of the important part in a backend service, which is usually not as exciting as this front-end effects, is to recognize actions, knowing that, for example, people pointing to something, recognizing different gestures, and using that for further processing.
Great. Any other questions from the audience?
Hi, I have a question. Thanks for the great presentation.
Thank you.
When developing these applications, how much time do you spend thinking about the silicon available on the market that will eventually deploy them, or do you have your own teams to work with to optimize the silicon in conjunction with the algos?
Yeah, so it's very, very crucial and very important to optimize for a mobile device. I show lots of curves there, and then most of the research also show like flops, numbers, and then theory of computation what needed for these networks. This is very far actually from the real-time scenarios on mobile device, and especially what time can take on specifically for different chips. You have to consider very well optimization of your model and then the application for the specific devices. You can apply or create even different models for specifically for some of the iOS, CPU, GPU, or DSP. They have different balance of optimization, but also you have to push forward in terms of hardware to make sure that something which could benefit very much on most of the networks and improvement of this application, that those layers and then those combination of layers are optimized very well in hardware. So it's between collaboration between hardware is very, very important.
But do you guys have your own kind of internal silicon expertise to guide you in this?
Yes, so definitely there are many people in Facebook who are expert actually on these silicons, and then and pushing forward collaboration with silicon vendors, as well as exploring other research aspects for improving the hardware itself.
One
So
more question over here on the left.
Yeah. Thank you very much. I hope.
Hi, I have a question for real-time post estimation.
Yes.
What kind of backbone are you use? Did you use FPN on it?
FPN?
Yeah, did you use FPN
Yes.
on? Okay, so what kind
So
of?
Mascar CNN using like Mascar CNN as it published, it has a segmentation head, key point head, detection head. It's a basic purpose of FPN. Networks. So especially the model itself, what we proposed and open sourced, it doesn't have, we didn't open source the FPN part, an optimization for that aspect. It's without FPN, you can run real-time key point estimation on mobile phone.
Okay, what kind of backbone are you use?
So backbone, we design our own backbone itself, which hopefully gonna be published later this summer. It's very specific, very optimized specifically for key point and Mascar CNN for mobile phone. But if you want to push forward, you can start with very efficient networks. What's out there, definitely would suggest like SqueezeNet or Disgustable ShuffleNet, MobileNet, and other networks.
Yeah, thank you.
Thanks.
Right. All right, let's give Peter another round of applause. Thank you.